Okay, so we're doing a second implicit differentiation example. So we're going to find dy dx for the equation. Okay, and our equation is going to be x cubed sine y plus y equals 4x plus 3. Okay, so remember the first step is you have to take the derivative of everything with respect to x. Okay, so let's split all that up. You're going to get the derivative with respect to x of x cubed times sine y plus the derivative with respect to x of y. That's going to be equal to the derivative with respect to x of 4x plus the derivative with respect to x of 3. Okay, so I wrote it all out. I'm taking my derivatives. Okay, so obviously the ones on the right-hand side are the easiest to deal with. What's the derivative of 3 going to be? What is the derivative of 3 going to be? 0. Yep, it goes away. Now, the derivative of 4x is easy to do. You could factor out the 4 using the constant multiple rule. This becomes 0. The derivative of x is 1, so you get 4 times 1, which is just 4. Okay, so on the right-hand side, you get 4. Nice. Because the derivative of 3 is 0. Use the constant multiple rule to take out the 4. The derivative of x is 1. 4 times 1 is 4. The right-hand side is a little more complicated. Now, it's going to be a little more complicated in particular because of this part right here. What rule am I going to have to use on this part? What derivative rule? Yes, I'm going to have to use the product rule. And I'm just going to point out here that the derivative of y with respect to x is just dy dx. So that one's easy to deal with. Okay, now the product rule is a little more complicated. Product rule says, well, you're going to have to take the derivative of the first one. So you're going to take the derivative of x cubed. You're going to multiply that by sine y. Then you're going to add to that x cubed times the derivative with respect to x of sine y. Okay, so that's a little more work. Okay, now there are two different derivatives you're going to have to work with. One of them is the derivative of x cubed with respect to x. That's just a regular derivative. The other one is the derivative of sine y with respect to x. That's going to be an implicit derivative. So let's do the regular derivative first. The derivative of x cubed with respect to x is just 3x squared. And that's going to be multiplied by sine y. Now, the derivative of sine y is a little more complicated. Sorry, the derivative of sine y with respect to x is more complicated. The independent variable is y, so I'm first going to take the derivative with respect to y of sine y. And then I'm going to multiply that by dy dx. And then don't forget that you have this other dy dx over here. Okay. So we can simplify things a little here. You get 3x squared sine y plus x cubed times, now the derivative of sine y with respect to y is cosine y. then you leave the dy dx. Let's move all this over. It's like all stuck. There we go, that looks a little better. Smooth this part too. Okay, I'll just erase it, move it. Okay. So now that I've taken all my derivatives, I need to isolate the dy dx's on one side. So notice these terms, these two terms right here have dy dx's. They're going to stay on the left-hand side of the equation. I'm going to subtract 3x squared sine y from both sides. So I'm going to have x cubed cosine y, and then I'm going to leave the dy dx in red. dy dx plus dy dx equals 4 minus 3x squared sine y. So to solve for dy dx, I'm going to factor it out. So I'm going to factor out dy dx. If I factor out dy dx, that's going to give me x cubed cosine y plus 1. And then what is this equal to? 4 minus 3x squared sine y. I can now divide both sides by x cubed cosine y plus 1, and I'll have solved for dy dx. So dy dx is going to be equal to 4 minus 3 x squared sine y divided by x cubed cosine y plus 1. This is my formula for the derivative. So if I was to take a point on the graph of my original function and plug those x and y values into this formula, I would get the slope of the tangent line at that point. So let's set that down. Plug x and y values into this to get the slope of the tangent line